Let's take a look at section 5.1. In section 5.1, we start looking at proofs in a little bit different way. We're going to be using what's called indirect reasoning, or maybe we should call it, say, what other people call proof by contradiction. And these proofs, well, let's go back to our standard conditional statement. P implies Q, okay. Remember what the truth table for this looks like. Pretend like those are straight lines, please. True, true, false, false. Q can be true, false, true or false. And P implies Q. True implies true, that's true. True implies false is false. False implies true is true. False implies false is true. Okay, when you're looking then at a conditional statement, let's get all these things pulled in here. Then the only time a conditional statement is false is here. A conditional statement P implies Q is only going to be false if P is true and Q is false. So when we do a proof by contradiction, what we basically want to do is to rule this situation out. Okay. And this is something you do. This is supposed to say rule out in the false case. This is something you do a lot. If you're doing little logic number puzzles like Sudoku or something, you'll put a 3 in a square and say, well, let's try a 3 and see how it works. And maybe putting a 3 in one square means that the square above it's got to be a 2, but you've already have a 2 in that row, so you can't do the 3. So basically what we're doing is we're ruling out this case. And if this doesn't happen, then the implication has to be true. So basically what a proof by contradiction does is we suppose that P is true and Q is false. And then we do direct reasoning, ordinary old deductions sort of stuff. And somewhere along the line, we're going to come up with some sort of contradiction. We get a statement that contradicts something that we already know is true. So that means once we get our contradiction, that means that this can't happen. Meaning that the only place the thing will be false doesn't happen. So P implies Q is true. Okay, so keep that in mind. We're going to do several proofs along those lines. Now let's just get some terms out of the way here. Parallel lines. And I'm not going to write down the exact definitions here. I'll just state them out loud. Parallel lines are lines in the same plane that do not intersect. Okay. Skew lines are lines that aren't in the same plane. And we'll usually represent them something like this. The idea is that this guy is perhaps below the slanted line. Okay. A transversal. When you have two lines, and they don't have to be parallel, I'm not going to draw them parallel here. But when you have two lines and they are crossed by a third line so that the intersection points are unique, okay, this point and that point aren't the same, then what you have is these two lines are crossed by a transversal. And generally, if we're going to call these two lines L and M, we usually call this line T. Now, a lot of angles are formed when we look at these things. So let me see if I can scoot everything down here a little bit. There are a lot of different angle forms here. Okay. Alternate angles. Alternate angles are angles that are on opposite sides of the transversal. Okay. Interior angles are angles that are between the two lines. Okay. So interior angles would be those four right there. Okay. Exterior angles would be angles that are on the outside of these two. In other words, that's exterior, that's exterior. Those four are exterior angles. Corresponding angles are angles that are on the same side of the transversal where one is interior and one is exterior. In other words, I'm going to number these guys here. Okay, so angle 1 and angle 6 are corresponding angles. Okay, 2, excuse me, that's a 5. I'm sorry, I just made a mistake there. Okay. 2 and 6 are as well. 3 and 7, 4 and 8. Now, lots of times we put these things together and we have things that are like alternate interior angles. These are angles that are on opposite sides of the transversal but are between the two lines. So this would be something like angle 3 and angle 6, angle 4 and angle 5. These things occur in pairs. Angle 3 is not an alternate interior angle. Angle 3, 6, and 5 are not alternate interior angles. Okay. Let's see. And we have, we might have exterior, alternate exterior angles as well. That could be angle like 2 and 7. They're exterior angles on opposite sides of the transversal. Okay. Another pair of alternate exterior angles, angle 1 and angle 8. Okay, so I'm assuming that you know these. If not, look at some examples, and we'll do some stuff as we go along here. Okay, let's do a few theorems here. Theorem 5.1. If two lines are cut by a transversal to form a pair of congruent alternate interior angles, then the lines are parallel. So one of the things about these indirect reasoning, these proof by contradictions, is they really don't lend themselves to two-column proofs at all. So this is paragraph type stuff. You need to write things down a little bit here. What we're going to do is and if you're going to do a proof by contradiction, then you should say so. And a proof by contradiction is we assume the hypothesis, two lines cut by a transversal forming congruent alternate interior angles, and we assume that the conclusion is false. So let's suppose that lines, I've got these guys have some names here, M and L are cut a transversal T, and since this is a T here, okay, so that angle 1 It's congruent to angle 2, and we should say here, as shown. So that means they're alternate interior angles. Okay, and we assume that this is not true, and the lines cut of this, and that L, M, L not parallel. Okay. Okay, I need to redraw this a little bit here, because the picture that I've gotten here, I grabbed right out of the book, is a picture of parallel lines. So if I'm assuming something's not parallel, I need to redraw the picture here. So it's going to look a little bit more like this. Here's line E. Whoops. Need lines here. Okay. Line M. Okay. Here's my transversal. And if these lines aren't parallel, then they're going to intersect somewhere. Okay. So in other words, let's let, oops, let P, well, just look at my notes every now and then. Okay, let's go back. I'm sorry. Okay, let's let lines M and L are cut by transversal T at points A and B, so that angle 1 is congruent to angle 2 as shown. Okay, and let's suppose further that M is not parallel to L. Parallel not to L. Okay, so let me redraw what my supposition is here. I'll get it right here. Here's M. Here's T, and here's L, and we're supposing that these two are not parallel. Okay. So here's M, here's L, here's T, here's angle 1, and here's angle 2, and this is going to be point A, and this is point B. Okay, now, if M is not parallel to L, they intersect at some point C. Okay, now, looks something like that. Yes, if you can read it. Okay, now from this picture, from everything we've drawn here, we have that, note that angle 1 is exterior, is an exterior angle for triangle ABC. Okay, and this means that we can use one of our theorems, which I had to go back and look up, 411, okay, that since this is an exterior angle, the measure of angle 1 has to be greater than, well, it's greater than the measure of angle C, but it's also greater than the measure of angle 2. Okay, now, wait a minute, that gives us a contradiction. This contradicts our assumption. Excuse me, let's not say assumption. This contradicts the given statement that angle 1 is congruent to angle 2. I mean, this was given to us. Okay. Hence, our assumption that M is not parallel to L is impossible. Okay. M must be parallel to L. And we put a little box signifying that I'm done with the proof. So you suppose it's not true and prove that that can't happen. Okay, here's a corollary here. Just to remember, corollaries are just little 1 or 2 step results from the previous one. Corollary 5.2 says if you have 2 lines and they're both perpendicular to the transversal, then they must be parallel. Well, I'm going to outline a proof for you. If these 2 lines are perpendicular to the transversal, then that's a right angle, and that's a right angle, or that's a right angle. Okay. Then that means I have alternate interior angles that are congruent. So they have to be parallel. A few more corollaries. If 2 lines cut by a transversal form, whoops, why does that? Form a pair of corresponding angles that are congruent, like angle 1 and 2 here. Okay. Then the lines are parallel. Well, what do you know? Angle 1, if it's the exterior, a pair of corresponding angles, one of them's going to be exterior. So it will form, well, there's an interior angle that's vertical to it. So angle 1 and angle 2 are congruent. Well, 1 and 3 are congruent because 3 is vertical. So that means 3 and 2 are congruent. I've got congruent alternate interior angles. So I have parallel lines. 5.4, something like 2 lines are cut by a transversal. And if they form a pair of supplementary interior angles on the same side of the transversal, like this guy here, then the lines are parallel. Well, so these 2 are supplementary. So 1 plus 2 180 degrees. Well, you know this. We know that the measure of angle 1 plus the measure of angle 3 is 180 degrees. Okay. So if these 2 add up to 180, these 2 add up to 180, I'm going to skip a little bit of a step here. That's enough to imply angle 2 and angle 3 have to be the same size, and their alternate interior angles congruent, so you have to have parallel lines. As I said, corollaries are just 1 or 2 steps. Now, back in the chapter 3, I think it was, maybe it was in 2, we assumed, well, actually in previous chapter 4, when we were doing triangles, we assumed a number of things, a number of postulates that lots of books don't assume. But you have to assume a few things, and Euclid, when he wrote the Elements, he made a number of assumptions, and the 5th postulate is what, Euclid's 5th postulate is what's called the parallel postulate. And it is really, really important. It is a big deal here. It says, given a line L, okay, which I've got drawn here, and a point P that's not on L, there's exactly one line M through P such that L and M are parallel. Okay. Now, this is not exactly how Euclid said it. Euclid said it something a little more strangely here, which I've got an English version of it here. It wasn't not written in Greek. Straight line falling on 2 straight lines. This is a transversal. Makes interior angles on the same side less than 2 right angles. The 2 straight lines meet on that side, which are the angles less than 2 right angles. Okay. So it's saying something like, if these 2 things add up to less than 180, then those guys are going to have to intersect. Well, the above statement, okay, we don't really write Euclid's fifth postulate down anymore. This statement is the one that most everybody uses. It's called Playfair's postulate, named after John Playfair, who published it in a presentation of Euclidean geometry in 1795. However, it dates back to about 400 something AD, or Common Era. This parallel postulate that there is there is exactly one line through a point not on the one parallel is sometimes called the Euclidean parallel postulate. And geometries where this is true are called Euclidean. And we tend to think that the space we live in is Euclidean, but not necessarily. There are other parallel postulates. Nikolai Lobachevsky was responsible for the Lobachevskian parallel postulate, and it basically says that given a line, I'll put it down here, okay, we have a line and a point not on the line, then there are at least two lines through this point parallel to the original. Well, that doesn't seem right, but that's another assumption. Actually, the Riemannian one here will do. This is from Bernard Riemann. Okay, and it's interesting. It says that there's no such things as parallel lines. No two lines in the same plane are parallel. Now this seems very strange, but we're going to do an example of this toward the end of the semester that actually makes a fair amount of sense. Okay. Lobachevskian geometry, in the case here where you have more than one parallel line, when you add up triangles, angles, you get less than 180 degrees. Riemannian geometry, when you add up the angles of a triangle, you get 180. In Euclid, you get something greater than 180. In Euclidean, you get things exactly equal to 180. Now, this parallel postulate was thought to be so obvious that for thousands of years people thought, well, they could just prove it, that they didn't have to assume that it was such an obvious thing, we could prove it, and it would follow from all the other postulates, but nobody ever quite did. There's really some pretty strange things that went along with this, and I might talk about them later when we get into the non-Euclidean geometry stuff later in the book. Okay, but we're going to assume that if we have a line and a point not on the line, then there's exactly one line through that point that's parallel. Okay, so we're going to assume that. So let's do a proof for 2 here. Theorem 5.5. This is a converse of Theorem 5.1. 5.1 said if you have congruent alternate interior angles, then the lines are parallel. 5.5 says if the lines are parallel, then you have congruent alternate interior angles. So we're going to prove this by an indirect method. So this is going to be proof, and I'm going to say this is by contradiction. In other words, we're going to suppose I have parallel lines, but that these two angles aren't congruent. So we're given two parallel lines. M and L, okay, cut by transversal T. Okay, and let's assume that the alternate interior angles that angle 1 is not congruent to angle 2. This means that these guys have different measures. Okay. And if their measures are different numbers, then one of them's got to be bigger than the other. So let's suppose, I don't know which one it is, but let's suppose that angle 1, whoops, is the larger angle. I'll get it right here. Okay, now we shouldn't say that angle 1's bigger than angle 2. We should say the measures are bigger. Okay. And for further, let's suppose I've got let P be the vertex, vertex of angle 1. Now, I should have named these differently, shouldn't I? I should have called this M and this L. Okay, so P is a point that's not on L. Okay. Oh, I'm getting ahead of myself here. Suppose angle 1 has larger measure than angle 2. Now, there is an angle, angle 3, at vertex P with the measure of angle 3 equal the measure of angle 2. Now, this is going to look funny because I'm trying to draw an impossible situation, so of course it looks funny. But angle 3 will be an angle here, so that angle 3 and angle 2 are congruent. Okay. Since angle 3 is congruent to angle 2, okay, we go back to what was our theorem 5.1. Theorem 5.1 says that the new line, the line forming angle 3 at point P, is parallel to this line on the bottom, L. Okay. Maybe we should give this line a name here, N. Okay. So N is parallel to L. Okay. M is parallel to L. Okay. And N is not the same as M because it makes two different angles here. This gives us a contradiction. This contradicts the parallel postulate. Okay. Only one line through P is parallel to L. Okay. So our assumption here is that angle 1 is not congruent to angle 2. Cannot happen. Angle 1 must be congruent to angle 2. I'm done here. Alternate interior angles have to be congruent, because if they weren't, I could find another line that gave me congruent alternate interior angles, which means I would have another parallel line, and there's only one. Okay, We have a bunch of corollaries here that are rather simple, that were like the corollaries to 5-1. And I'll just kind of talk a little bit away through this. If you have two parallel lines, oops, and we have that a line is perpendicular to one of those two parallel lines, it must be perpendicular to the other. Well, if these two lines on top are perpendicular, then I've got right angles all the way around. Particularly, I've got one right there. And if these two lines are parallel, this angle and this angle are alternate interior angles. They have to be congruent. So that has to be perpendicular, which means that has to be a right angle, which means those two things have to be perpendicular. 5-7. I'm going to prove one of these after a while here. If two parallel lines are cut by a transversal, then each pair of corresponding angles is congruent. Well, what you know is if two parallel lines are cut by a transversal, alternate interior angles must be congruent, and this interior angle is vertical to that one, so those two must be congruent. So those two have to be. And 5-8, if you have two parallel lines cut by transversal, and you're looking at both pairs of interior angles on the same side of the transversal as supplementary. So you'd want to say that this angle and this angle are supplementary. Well, you know that A and C are supplementary because their exterior sides form a straight line. Okay? And you know that C and B are congruent. So A plus C is 180 measure. Okay. C and B have the same measure, so A plus B must be 180 as well. Okay, let's do a few from the book now because it's pretty straightforward stuff here. It's 248, 23 through 28. We have a few angles given to us, an 80-degree angle and a 50-degree angle, and sides that are marked with the same type of arrow are parallel. So those guys are parallel, and those guys are parallel. Okay. I'm going to go ahead and write down some things I already know here, whether we need them or not. If this is 80, then that's 100. Okay. Now, let's see. What do we know about this? I'm going to extend a few things here. Okay. Here I have two lines. Okay, this L and M maybe, and they're cut by a transversal, BC. Okay. And this angle here at E, that 80-degree angle, and this angle are, and this angle are corresponding angles. So that has to be 80. Okay. Angle B is corresponding to angle FEC, and parallel lines mean that the angles have to be congruent. Now, let's go with, BDF, BDF. Yeah, let's do BDF now. Okay. Now, BC, okay, Here I have a line N and a line O, okay, and they're parallel. And 80, this angle here is 80, and this angle is, well, these two angles are interior angles on the same side of this transversal, so they have to be supplementary. So BDF and angle B have to add up to 180 degrees, so this one has to be 100 degrees. Okay. And but once you have that, this has to be 80, because ADF and BDF add up to 180, or else you can have ADF and B are corresponding angles. Okay. AFD, well, AFD, if this is 80, I want to do this way, AFD. If this is 50 and this is 80, so it's going to be 180 degrees minus 130 degrees. This will be 50 degrees. Okay. DFE, DFE. Let's see. These are, this angle and this angle are alternate interior angles with some parallel lines. And angle C, well, let's see. What do we got here? Okay. C is this angle and this angle are corresponding angles, so it has to be 50. Okay. Okay, I hope you can see that. So let's prove corollary 5-7. I actually kind of thumbed my way around it here. Let's see if we can't prove this, and maybe let's do a two-column proof. Okay. So let's give some names here. Let's call my two parallel lines L and M, and my transversal T. Okay. And let's just look at a couple of corresponding angles here. Well, let's look at, let's call this angle A, this angle B. Okay, so we're given lines L parallel to line M, and transversal T, with angle A, angle B corresponding angles as shown. Okay. What we want to prove is that angle A, oops, is congruent angle B. Okay. So let's start by putting in the, well, let's start by something else here. Okay. Let's start by saying that angle A is congruent to angle, let's give this guy a name C here. Okay. And we didn't put C down, but C is going, this is going to be the reason. Vertical. Angles are congruent. Okay. Probably should be a little more careful here. We should say that angle A is the exterior angle. Let C be the CB vertical to angle A. Okay. Now, statement 2. Let's say that L is parallel to M. Okay, and this is 1. Reason 2 is given. 3 is going to be angle C is congruent to angle B. Excuse me. And that's going to be, well, this previous theorem we had, right? 5-5. When parallel lines are cut by transversals, alternate interior angles are congruent. Let's just say theorem 5-5. Okay. Well, A is congruent to C, C is congruent to B, so that means angle A is congruent to angle B. And this is what's called the transitive property. And I believe we're done there. Okay. So I probably should say a little bit more. I should have said let A be the exterior angle in the pair. Then it's the vertical angle. Let C be the vertical angle for A. Okay. So those two are going to be congruent because vertical angles are congruent. Okay. These two lines are parallel. That means C and B have to be congruent. And then if A and C are the same size and C and B are the same size, then A and B are the same size. That's transitive property. Okay, well, I hope this helps you on this section. It's not too bad. Uh, I think that it's pretty straightforward.